Hello and welcome to the Toronto Geometry Colloquium. This is a weekly web series all about geometry processing.
This colloquium aims at promoting young researchers and researchers from traditionally underrepresented communities. Every week, we will have an opener talking about their cutting-edge research for 10 minutes, followed by a headliner giving us a keynote presentation.
Welcome back, everybody, for the first episode and yet another season of the Toronto Geometry Colloquium. We had a nice, long, relaxing break, and we hope you've had one too, but we have a great schedule and lineup for this semester. I hope you've seen it online. If you haven't, be sure to follow us on Twitter to keep up to date with the latest news regarding our colloquium. And we'd especially like to thank you guys, our audience, for all sticking with us through these weird, difficult times, but also times where we find new ways of coming together and learning about each other's works. So thank you for sticking with us through that. And today we have a really great session lined up. Our first speaker comes all the way from the Iran University of Science and Technology. He's a second-year master's student and his work deals in the very challenging field of topology optimization. Specifically, his most recent paper provides a deep learning-based approach for determining how to best distribute material such that the resulting structure satisfies a certain set of criteria. These criteria can be elasticity, base stiffness, maybe you want it to be a certain stiffness or something like that. He may be applying for a PhD position at your lab soon, so keep an eye out for his application. And his most recent work was published at the Symposium of Computational Fabrication last year. Please welcome Nikan Doosti.
Okay, thank you for such a kind introduction. So I just present it. Just a second. Okay, so let's start. Okay. We showcase our design representation by solving the minimum compliance topology optimization problem. This problem seeks to find the stiffest possible structure to support the applied forces without exceeding a weight budget. Conventional methods for minimizing compliance suffer from the well-known checkerboard problem. They generate non-physical design with high-frequency checkerboard pattern. To prevent this from happening, a mesh-based smoothing filter is necessary. On the other hand, increasing the radius of a smoothing filter can over-smooth the designs and increase compliance, which is not desired. To obtain more intricate design that have lower compliance as our objective function, we need to use larger meshes if we use fixed filtering. The main issue here is that by increasing the mesh size, it heavily increases the computational cost of the solving problem. And by more intricate, we usually mean more holes and more branches in the design. There are different methods of approaching to this topic, which explicit representation is closest to our line of work. In this work, to map the input domain, which are the coordinates of a mesh to the target variable, a query function is needed. Neural network as general function approximators can learn this mapping with a good generalization and efficiency. There is a new trend in which a neural network is trying to fit solely to a single signal. In this direction, the input is a fixed mesh grid and the output is the point-wise evaluation of the target function, which could be an image, audio, and so on. After a successful training, the neural network accurately learns the target function, and since they are continuous and differentiable, they can replace original target function. The problem here is that in practice, neural networks can't learn the high frequencies, such as edges in images. And to fix that issue and enable models to learn high frequency functions too, Fourier features have been studied to map the low dimensional input to higher dimension. To do so, the pipeline would be exactly the same as before, and the only difference is that before passing input coordinates to a neural network, use this mapping. We are particularly interested in the value of sigma as the main hyperparameter in our work. Hyperparameter tuning usually is a necessary step in training deep learning models, and this might be the reason that discussion around using sigma is limited to the idea that it has to be tuned to a specific value. In that matter, using lower values lead to oversmoothed or underfitted model, and higher values lead to a noisy or overfitted model. So the best value is always a middle point value. We can deal with sigma similar to the way it has been introduced in prior works and only tune it to find the best solution with lowest objective value, such as 2D image fitting as we saw in previous slide. Here we can see that using very low or very high sigma will increase compliance by over-smoothing or making the design noisy. So there's again a middle point that obtains a low compliance, which is again desired. To parameterize our problem, use the same pipeline as before with Fourier features, and the goal is to train the model to learn the mapping from input mesh grid to the design variable, which is density field in case of topology optimization, which we annotated it with rho here. And different authors have already adopted neural design parameterization before us in different ways. For instance, we can see here a convolutional neural network has been used to learn this mapping. In this work, multi-layer perceptron or coordinate-based neural network has replaced the convolutional neural network, but still there is no frequency prior, such as Fourier features. And maybe the closest to our work, authors here used an coordinate-based meshless method, but they still treat the frequencies as a fixed hyperparameter, similar to image processing we showed in earlier slides. So as our main contribution, we demonstrate that sigma has much greater power. It can be used to tune the spatial frequency of the design continuously. In particular, by carefully setting the value of sigma, we can avoid checkerboards and yet still produce a highly detailed design. This observation enables us to remove the conventional mesh-based smoothing filter in all of our experiments and only rely on Fourier features to control the smoothing level of the designs. Using this sort of parameterization gives us the ability to have a fully differentiable self-supervised pipeline. It includes first the neural design parameterization that outputs a density field that is being evaluated using conventional voxel-based solver to compute compliance J as our main objective function. To update theta, the weights and biases of the neural network, we use sensitivity analysis, the analytical derivative of the compliance with respect to density field, and autodiff. Here we show that not only sigma replaces the explicit mesh-based filtering, it can also represent a continuous filter in sub-voxel level. For instance, we can use small values of sigma to obtain a smooth design similar to mesh-based filtering with radius larger than 1. We even can go below a voxel by using a large sigma values to obtain intricate designs. Once more, to obtain more intricate design that have lower compliance, we need to go for larger meshes that increase the computational time. Today, there is a large gap between what hardware demands and what computational models can compute. To close this gap, simple upsampling of the design is desired. The important question here is that, can we use our design representation to emulate higher resolution designs while using a coarse mesh? Well, the answer is yes. And here we evaluate the quality of designs upsampled to a fine mesh by measuring how much a traditional topology optimizer can improve the design. If the design was nearly optimal, this improvement will be small. So to show this, we first start by we use a coarse mesh and large sigma to obtain an intricate design. So using our proposed method, we expect to get a design similar to this, which we consider it as an intricate one. Then we interpolate it to a finer mesh using basic interpolation methods such as bilinear. And now here, using voxel-based solver, we expect that this solver either can make the design better by making it more intricate, or can make it smoother, or won't be able to change it and would have a similar result to the initialized solution. What we found out that we always get this similar behavior if we use a large sigma and then interpolate it to a fine mesh. So this is the expected pipeline by using these values. And this means that higher sigma means finer mesh in our design. For example, here we can see that the relation between optimality of the initialized solution from our method and the target mesh size for two cases. Sigma equals to as a small value, it should fit a small meshes after interpolation. And we can see that the lowest difference degradation or improvement in compliance happens for lower resolutions when sigma value is small, and the opposite also happens for sigma equals 9, which demonstrates a large value for sigma. And again, the difference is small for larger resolutions. And to showcase an example that the initialized solution or the solution our method obtained is not optimal, we consider this example with sigma 2 that initialized density is smooth, and when we interpolate it to a large resolution, the traditional solver starts to add more details to the design, as we can see here in the colored boxes. And to compare our result with other methods, we here intentionally treated sigma as a fixed hyperparameter because parameters treated as the same way. And we can see even though we obtain more intricate design, our compliance values are competitive. And for future works, we can employ better optimizer because at the moment we are using Adam and it's a lot of iterations. Our upsampling upper bound is dependent on the mesh size we choose for our voxel-based solver. And we can also control the frequency priors, for instance, controlling the lower bound of Fourier features to obtain a bone-like structure, which is an interesting feature in topology optimization. And that's it. Thank you for this opportunity and thank you for your attention.
Thank you very much for that talk, Nikan. As usual, we're going to have a joint Q&A session at the end. So now we're going to move on to our headline speaker. Our headline speaker comes a little close to home for us. You must have heard his voice for at least 2 years now in this weekly colloquium. He's just wrapping up his PhD at the University of Toronto, so he's one of us. And he's definitely the role model, star student, what have you, that all of the grad students in our lab strive to be. At least I do, I strive to be like him. So many publications to his name. You might know him from his very recent work that describes how to use multigrid on irregular domains, like on a triangle mesh instead of the boring old standard grid multigrid. Maybe you've read his SIGGRAPH course that provides a friendly introduction to deep learning on meshes. His work has addressed many problems in the noble pursuit of artistic 3D content creation, and he's soon to be available on the job market. So if you're a university or research institution that sees this and hasn't called him up yet, TikTok, you better hurry it up. Please welcome Derek Liu.
Thank you, Othman, for this wonderful introduction. So let me share my screen. Yeah, to me, this is really, really exciting to be here. Yeah, I was like the part of organizing teams and watched so many great talks. And then I also always want to be part of the speaker lineup. And today is the day I finally have time to contribute to this colloquium by sharing my research. So without further ado, let's jump right into it. So today we're going to take a look at a few examples of how we can make 3D content creation faster and easier. But why we're doing that? So imagine in the near future, if you turn on your TV during some holiday season, and probably due to some variants of COVID-19 or COVID-20, the city is still in a lockdown situation. So in this case, if you really want to, for example, catch up with your friends or meet with your parents, what you can do is probably you can only turn on your laptop and set out a video call with them, which is not really satisfying. So in the future, perhaps a more ideal situation is probably you can put on your VR headset and you can really feel that your dad is standing at the same virtual space as you and talk to you face to face. And in addition to that, you can also go to some museum or go to a zoo together in the metaverse to really have a great time. And although what I described here sounds a little bit like a science fiction, but I want to point out that this is something that is happening today. Today, we have more and more new virtual experiences. For example, we can all listen to the live concert of Justin Bieber in the metaverse. We can also remotely control a factory, or we can communicate with our remote colleagues in the virtual reality. And to support all these virtual experiences, the hardware is catching up. Like we have the VR treadmill for us to really run in the virtual world without moving physically. And we also have new haptic devices for us to really feel the touch from the virtual world. But in order to really pursue this dream to democratize the metaverse, there's still a big bottleneck, which is in the 3D content creation. So basically, if you want to create 3D contents to support, for example, this live concert, if you want to create a car, it may take days of work from a professional modeler. And if you really want to create a detailed 3D character that you can manipulate in this virtual reality, then it may take months of work of a modeler. And furthermore, if you want to create like a 3D world, like a large 3D map for all the participants to kind of walk around the city to feel the vibe, then depending on the size of the city, it may take years of work of a modeler. And the reason why 3D modeling is still so time consuming is because we're still at the stone age of 3D modeling. So in this example, you're seeing like a professional modeler using a technique called the subdivision services to model this digital character. And you can see that this operation is still very low level and very time consuming to model such a complex character. And if you want to get a feeling of how tedious that is, you can think of it as 2D analog. So what you see earlier is nothing but editing a single image by manipulating the color of individual pixels one by one, until you get the image you want. And you can imagine if this is the only way that we can model 2D image at this moment, I don't think you'll be using something like Instagram to share photo on a daily basis. So, and another reason why 3D modeling is still a bottleneck is because even if we are willing to spend, I don't know, months to create a shape we want, we probably will still have some difficulties to create that. That is because existing modeling tools are reserved for professional modelers. In other words, they require years of training to know how to use them to create the shape we want. So for a general public like me, even though if I want to create like a beautiful car, I may still have difficulties to use existing tools to create them. So my research really wants to tackle this problem. I want to make 3D content creation becomes a thing that is accessible to everyone. So we have seen like beautiful revolution to the image editing, starting from those low-level tools. We now have very easy to use tools such as Adobe Photoshop, and I want to make the same thing happen in 3D. I want to turn this low-level 3D modeling operations into something that's very easy to use for general public. And the approach I want to take here is the data-driven method. And the reason I'm looking to data-driven method at this moment is because compared to, for example, 10 years ago, right now is a great timing to look into data-driven method because it is the first time we have massive amount of geometric data. And in addition to like static geometric data, we also have more and more editable models. For example, like the technical term, it will call like parametric models or procedural models. But basically, these are models that have some intuitive parameters that we can tune. For example, take this building as an input, we can make this building shorter, and this procedural model will make the change accordingly. And we can also make it wider and we'll make a reasonable change like this. And so I imagine in the future modeling, we won't be start from nothing. We won't start from a sphere or the cube. We will actually start modeling a shape by first finding a shape that similar to what we want to create. For example, we can find a detailed bunny like this one, or this can be some editable model you see earlier. And after we find the shape we want, then we'll provide some algorithm, some geometric data to learn from. So this method can be some neural network or something else. And then after some processing time, this algorithm will basically make this last mileage for us and create the shape that we really want to create. So I imagine this is like the future of data-driven 3D modeling. And today we're going to take a look at a few examples addressing this pipeline. For example, we're going to take two examples, the subdivision and the 3D stylization. These are two examples of data-driven modeling method. And we're also going to take a look at a scalable solver, which can make the data-driven processing pipeline faster. So let's first look into the first one, the neural subdivision. So subdivision is a very popular technique in modeling. And intuitively speaking, it's just like take a coarse shape as an input and will recursively upsample this geometry and manipulate this geometry so that after a bunch of subdivision iterations, it becomes a smooth and high resolution shape. And if you remember the video we saw earlier, it is basically a professional modeler using subdivision to model a shape. And this technique consists of two very simple steps. The first step is just to add more vertices, add more triangles to this mesh. And the second step is to actually move the vertex positions of this model according to some predetermined rules, such as some weighted average. And you can recursively applying these two steps. And if you apply infinite amount of times, then you end up getting something called a limit surface, which is basically a smooth and high resolution shape starting from this coarse shape. So based on these two procedures, you probably can understand why subdivision is a very, very nice tool if you want to create something that's smooth, because take this square as the input. If you want to turn it into this spherical-like shape, all you need to do is just to continue hitting the subdivide button. That's it, and you'll be able to get a smooth shape out of it. But imagine if you want to create some complex 3D shape with a lot of sharp creases, sharp features highlighted in green here, then subdivision becomes something that's a little bit harder to use because you have to manually tweak the parameters of the subdivision in order to preserve those sharp features. So this motivates us to study the problem of neural subdivision. Basically, we try to train a neural network so that it can learn how to subdivide the shape differently for different parts, so that we don't need to manually tweak the subdivision parameter to preserve the features. We can leverage the neural network to learn how to preserve the feature and subdivide the shape for us. So in this case, we are subdividing the King Kong with a classic method. You can see that it's kind of smooths out these features, but if we use the neural subdivision, we can better preserve those features such as eyes and the nose of this King Kong model. And to train such a network, we have to talk about three different things, like what is the data, how can we design a network, and what is the loss function. So first, let's look at the data. So ideally, if we want to train a subdivision network, we hope to have many, many pairs of low resolution shape and the subdivide ground truth shape. If we have many, many of these pairs, then we can simply set up a training setup to subdivide the shape into this ground truth one. But unfortunately, even today, we still don't have a data set like this. So in this neural subdivision, we have to generate the trained data ourselves. And to generate that, we propose a self-supervised training setup for the neural subdivision. Basically, we start by taking a good-looking, highly detailed shape from some existing geometric data. We just need to take this one shape, and we treat this as a ground truth shape. And we will do random mesh simplification to simplify this ground truth shape into many low-resolution bunnies with different resolution and different triangulation. And once we have that coarse bunny, then we'll take that as the input to the network, and the network will output a subdivide model, which is like a higher resolution version of that bunny. And our network can do the same thing as a classic subdivision. We can recursively apply our network to get higher and higher resolution. And until we get to our final resolution, then we will compare that with the ground truth bunny we used to generate those simplified input bunny. And I just want to point out that these two measures usually don't have the same connectivity. So you have to find some new ways of properly comparing both. And once you have this loss function, then we'll backpropagate the loss to the network to update the parameter. And for the sake of our time, today we're going to take a deeper dive to how can we design this network. So this network is actually operating on the triangle mesh. And learning on meshes itself is actually a pretty hard problem. One reason is because triangle mesh have many natural variations. For example, a triangle mesh can have a same resolution, but with a different triangulation. It can also have a different resolution, or it can have a different orientation. And if you want to do machine learning on meshes, you have to handle these natural variations happening in triangle meshes. You cannot make assumptions that, okay, I have to have this specific triangulation with specific resolution. So we have to handle all these variations. And another reason why learning on meshes is hard is because it makes a lot of convenient machine learning operators hard to define on meshes. Like one example is the convolution. So convolution, we know that this is like a very crucial operator when we want to build an image CNN for classification. And we know that we can just take a bunch of pixels and define a convolution kernel like the one shown here. But if you want to generalize that convolution to meshes, things start becoming a little bit tricky. It is unclear how can we generalize the notion of convolution here. And one naive way is probably just, okay, just take a bunch of vertices and define a convolution kernel like this. But you'll immediately encounter a problem that the same vertex in the model may have different numbers of neighbors for different places in the model. So in other words, if you want to define CNN using this way, you cannot do that because it means that the size of your convolution filter is not fixed. And this makes us difficult to define CNN. And because of that reason, people are considering different alternative representation to represent 3D shapes. For example, one popular one is to represent 3D shape using voxels. And this is a regular representation, which is easy to define convolution and pooling and that kind of thing. But you can see that it is not a very good approximation of a smooth shape. And people may treat it as like a just general graph, and you apply some graph neural net, but this representation loses the manifold information. In other words, you don't know whether this is a graph of a social network or this is a graph of a surface triangle mesh. And having this information will really make a difference. And another popular representation is just to represent the shape using a bunch of point clouds and apply point nets. But this is even worse because they not only lose the manifold information, you also lose the connectivity. So the key idea of our work is to say that we are not going to rely on alternative representation. We're going to do learning directly on surface triangle meshes. And particularly, the basic element we look at is something called a half flap, which is nothing but two triangles associated to each directed edge. And if you look at this representation, you'll see many benefits. Like one of them is that if you want to define convolution on vertices, this representation always have 4 vertices. So it means that if you want to define a convolution kernel, the size is always equals to 4, which makes it easy to define a convolution operation. And another feature that is more important is that this 4 vertices actually have a canonical ordering between them, like the black and the blue and the green and the red. And because we have this canonical ordering, we can define something that's very crucial to the neural subdivision, which is the local coordinate system. And that local coordinate system is the key to make this network invariant to rigid motions. So let me give you a simple example to explain this. So imagine you want to design a subdivision network based on this half flaps. And then let's say your input features are XYZ locations of each vertex. And you train your subdivision network to subdivide a cow at this location. And after your training, you can perfect fit the train data. But during test time, if you encounter a cow with a different orientation, and if you apply the same network, actually, this is the result you will get, which is not that satisfying. And the reason is because if your cow rotated, your half flap also gets rotated. And during this, because of this rotation, the input location of each vertex will change. Therefore, from the perspective of a network, it is seeing completely 2 different shapes. Although from a human perspective, we see that, oh, they are actually the same cow, just with a different rotation, but the network will have difficulty to figure that out. But if we have a local coordinate system, as we described earlier, all you need to do is just to do a coordinate transformation to represent every features like vertex locations using this local coordinate system. And once you do that, no matter how you rotate or translate the cow to a different place in the world, the coordinate will also get rotated and translate at the same with the mesh. Therefore, the vertex location using this local coordinate system will remain the same. Therefore, if you use this coordinate transformation and train the subdivision, and no matter how you translate or rotate the model, you always get this beautiful result because it is invariant to rigid motion. So that's basically how we handle a mesh with different orientations. And for different resolution, we have to take a look at the architecture of the model. So we designed the network mimicking the structure of classic subdivision. We also consist of two simple steps. The first step is the same. We just add more triangles, add more vertices to the mesh. And the second step is that when we will take each half lap of the mesh and then pass it through a network to predict some output displacement vector. And then we will copy paste that displacement vector to a mesh. And then after that, we'll take another half lap of the mesh and again, pass it through a network and get another displacement. And then we'll do the same thing. We'll copy paste that to the mesh. And we'll do this process for all the half laps in the mesh. So we get a bunch of displacement vectors on the model. And then we'll do a global average, like merge this displacement and average them in to produce a single displacement vector for each vertex. And we'll use that to move the model. And you can see that the process we describe here make no assumption on the number of vertices or number of faces or number of half laps. This operation can easily handle mesh with different resolution. You just need to apply more iterations of this operation, then you can handle a mesh with high resolution. So therefore, that's how we can handle mesh with different resolutions. And to handle different triangulation, we basically rely on the fact that we generate the training data by random mass simplification. So during training, the network already sees many shapes of the same shape with different triangulations. So it can automatically learn how to be robust to different triangulations. And that's basically how we handle that. And that's basically all we need to train a subdivision model, and we can start playing with it. So in this example, you're seeing like some test time input we use to test the model, and these models are very different. They are not existing in the training data. And if we apply our neural subdivision network on these models, you can see that it generalizes pretty well that it can successfully subdivide all these models to this feature-preserving smooth geometry. And you may wonder, how many shapes do I need to train a network so that it has such a great generalizability? The answer is 1. We only need a single shape here to train the model, and we will be able to generalize to all these models that are completely different from the training shape. And we can also do the same thing. We can take this elephant with a T-pose, we can train on this T-pose and test on all these different poses. And again, we can still generalize to all of them. So the fact that we are so good at like data efficient, we only need a single shape to train. We're so good at generalization, give us a very new way of doing subdivision, which is we call it data-driven subdivision. Basically, start from this input, a user simply need to provide this network a different training data. For example, we can provide the network a smooth elephant, and the network will be biased towards the shape user provided, so that it will create a smooth chair after the subdivision. But if the user input is some meme object with a lot of sharp features and flat faces, then the subdivision network will try to preserve those features after the subdivision. And another example is that if you train on noisy shape, then as expected, the network will also make this input model into some noisy output subdivided model. And that basically concludes our first example of how can we leverage data to transform this important subdivision operation, starting from some coarse shape. Then we don't need any user input. We just need to provide the training data, and it will be able to output something that's feature preserving and echoes the style of the data we provided. And now let's take a look at the second example of the stylization. So in this stylization, we study the problem of how can we turn a content geometry like this dragon into the style of another shape, such as a cube here. And for clarity, we're going to take a deeper dive to this cube for now. And the reason is because cubic style is actually a very important artistic style across the art history. So in this slide, you're seeing many cubic sculptures. You can see that artists will tend to preserve those important features from the content geometry, such as the eyes and the hairs, so that we can recognize the subject of the sculpture. But if you step back and take a look at the shape from the global perspective, you'll notice that these cubic sculptures look like a generalized version of a cube. And this effect is what we are going to achieve with our algorithm. And another reason why we studied stylization is because it is a very important tool for content creation. For example, in 2D, we can now take a picture of a cat, and then we can have so many 2D stylization filters to turn this cat into so many different shapes, so many different images like this. And it has been a very important content creation tool for people to, for example, share photos on the Instagram. But in 3D, if you want to create this cubic stylized digital character, it is still a very difficult process. It is usually done manually. So this basically motivates us to study how we can make 3D stylization becomes an easier problem. And the reason why 3D stylization is still very difficult is because defining the style is something that's very hard, because it ties to how we humans perceive the geometry, and it's something that's not that trivial to write down an algorithm to do that. So let me give you a simple example. If I hand you a cube, how would you characterize the style of a cube? So one way you may want to characterize the style of a cube is probably you take a look at the vertices or the corners of a cube. And you will notice that each corner actually have 3 90-degree angles associated with it. And you can probably treat this as a definition of cubic style. And let's give it a try. If we treat this as a definition and want to transfer that definition to this coarse bunny, and a possible algorithm is probably you can turn this bunny into this, which by our definition, it is a cubic style bunny because almost everywhere on this bunny surface have this 90-degree corners. But if you take a look at the sculpture you saw earlier, I don't think you will agree that these two share the same style. So what we want to achieve is something like this. We start from this bunny. We can preserve the features like the eyes and the ears, but make the general global appearance of the bunny look like a cube. And to achieve that, our key ideas is to characterize the style of a 3D shape using not the vertices and the corners, but we want to use the surface normals of the shape. And if this style shape is a cube, then it means that the surface normal has to be something like 0, 0, 1, 0, 1, 0. They are axis-aligned vectors. And this perspective enables us to use many nice mathematical tools to achieve this. And particularly, the one we use here is the L1 norm, because the L1 norm of an axis-aligned vectors is always smaller than the L1 norm of a non-axis-aligned vectors, because the axis-aligned vectors like 1, 0, 0 is sparse. Therefore, we can actually build an optimization algorithm by minimizing, for each vertex, we're minimizing the L1 norm of the normal vectors of the output mesh. But remember earlier, like we not just want to make things look like a cube, we also want to preserve some features from the content shape. So we also add another regularization to make sure the input looks like the output. And in particular, the regularization we use here is something called ARAP energy. Basically, for each edge, ij, we first collect a bunch of input edge vectors and collect a bunch of output edge vectors. And we also find a rotation so that the rotated input edge vectors are the same as the output edge vectors. And it intuitively means that locally, we want the shape to look like differ by a rigid transformation. And this is basically one way of saying that we want the input shape to look like an output shape. But if you look at this energy, you'll notice that there's a problem here. This energy is actually very difficult to optimize. And the reason is like this output vertex positions U is our optimization variable, but this normal vectors of the output mesh is a nonlinear function with respect to the output vertices. So in other words, this term will make this entire expression nonlinear, and this is usually harder to optimize. So our trick is that we perform a change of variables to replace that output normal vectors with a rotation times the normal vectors of the input mesh. And the reason that we can do this is because for any unit vector, such as the output normals, we can always represent that as a rotation times another input vector. Therefore, we can do this change of variables to represent our output a normal vector. And this small change of variable actually makes a huge difference because now the entire expression is a linear respect to our output mesh vertices. Therefore, we can use some very easy and efficient optimization tools such as coordinate descent to minimize this energy. Basically, the first step is that we fix all the output vertices U. We optimize the rotation, the RK here. And this can be solved efficiently using ADMM. And for the next step, we basically fix all the rotation we compute previously, and then compute the output vertex locations. And this can be easily done by solving a single linear system. And our algorithm basically iterates between these two steps until we converge. And that is basically everything we need in order to turn this cubed cow into a cubic cow like this. And this algorithm also runs super efficient. Like in this video, you're seeing the real-time screen capture of me using this algorithm to stylizing this frog. And you can see that it is actually an interactive algorithm. And we can also add a lot of different artistic controls to this algorithm. For example, we control the cubeness of the shape. We can turn this less cubic bunny or very cubic bunny. We can also leverage the fact that L1 norm depends on the orientation of the shape. So we can rotate the mesh and then apply this algorithm, and we can get many different cubic stylization shapes. We can also add constraint to the model. So in this case, we are constraining the legs of the frog to lie on two planes. So we can actually create a table cleaner shown on the right. And we can also do something more interesting. We can generalize to stylization beyond the cube. So in this case, we take some gray shape as the input, and the user provides this algorithm some target style it wants to achieve. And our algorithm is able to generalize to these style shapes and then turn this input geometry into the style prescribed by the green shapes. So it means that right now we actually have a very easy to use data-driven stylization method. Starting from input geometry, all user need to do is just to provide this algorithm different style shapes. And this algorithm can automatically turn this input shape into all these different styles without any manual tuning. So that is basically concludes our second example, which is a very easy to use data-driven modeling method to turn the shape into a different style. This algorithm is great, but actually it has a small issue that it runs very slow if your input mesh has a high resolution. So in this case, I'm playing the video. It is a real-time screen capture of me cubifying this high-resolution dragon. And you will probably question me, oh, am I playing the video? And the reason is because this algorithm runs very slow if your mesh is high resolution. So I'm actually optimizing it, but like each iteration takes so long, so it looks like a static figure. And the reason of that runtime is because the global step, the part we solve the linear system, is actually take a lot of time when we want to operate on a high resolution model. For example, if our input is a highly detailed fossil scan with millions of vertices, then solving a single linear system with Cholesky will take us around 5 minutes, which is basically too slow if you're considering real-time or interactive applications. And not just content creation, like linear solver is actually a bottleneck of a lot of other geometry processing tasks, for example, solving PDEs or doing simulation. So this motivates us to study whether we can invent some solvers that are more scalable so that we can accelerate content creation and also other geometry processing tasks. And if you simply Google scalable solvers online, probably the method you'll find is something called a multigrid method. And because multigrid method is actually one of the most scalable solver today. For example, it has been deployed to solve extremely large scale computation problem like these two papers. They use multigrid method to solve problem that was billions of degrees of freedom, which is like many orders of magnitude larger than the problem we consider in geometry processing. And the reason why these scientific computing community, they like multigrid method is because it is really very scalable. So if you just implement this multigrid serially, it will scale linear time with respect to the number of degrees of freedom, which is perhaps the best you can get. But more appealing is that multigrid can be parallelized. And if you are working on a super large, like super powerful computer, and you parallelize your multigrid really well, theoretically, multigrid can run in constant time for solving any linear system. This is why, like on large scale computation, people prefer to use parallel multigrid to solve their problem. But if you want to use multigrid for our surface triangle mesh, things become a little bit tricky because most of the multigrid methods so far, they're only defined on grids, like for example, 2D regular grids, 3D voxel grid, or some generalized version of a grid. And if you want to do multigrid on triangle mesh, like the one shown here, unfortunately, there's not a great solution here. And so to understand why defining multigrid on curved surface is hard, let's have a very, very brief introduction to the multigrid. So this is a class of solvers that are designed to solve a linear system, AX equals to B. And to begin the solver, you have to first build a hierarchy representation of your domain. For example, if you work on 2D grid, it means that the hierarchy means that the 2D grid with different resolutions. And once you have that, then you will provide this multigrid solver an initial guess, like the xi here. And then you will first compute the residual of this solution. And you will restrict this residual down to the low resolution. And in here, you will do some solve here to get the update vector to your solution. And then you will then interpolate the solution back to the original resolution and then use that update, the delta x, to actually update your solution. And the multigrid basically run this V cycle for multiple iterations until it converge. And within this kind of procedures, the most important ingredients are how can you define the hierarchy of your domain and how can you do this restriction and interpolation operator. And if you understand this, then you probably can already know like why people love to define multigrid on grids. And the reason is because it is easy to define the hierarchy of your domain. For example, on the left, we see a fine mesh, a fine grid, and you can simply simplify your grid into this. And then it is also super easy if you want to define interpolation. For example, you can just overlay each other, and then you take some signals from your low resolution grid. And if you want to determine a solution on the high resolution grid, you can simply do something like bilinear interpolation, and that's it. But if you want to do the same thing on curved surfaces, and things will become a little bit tricky. So take this mushroom as the example. And first, for clarity purposes, we are going to take a look at a single slice of that mushroom. So it will look something like this. And let's say we have some simplification algorithm to decimate the bunny to a low resolution. You may get a coarse slice of the bunny, a coarse slice of this mushroom like this. And you will immediately see an issue here that these two meshes are not perfectly aligned with each other. So in other words, it is not that easy to define an interpolation operator back and forth between this low resolution and fine mesh. And you can also come up with some naive solutions. For example, you can match the closest point. For example, like for each mesh, for each point on the fine mesh, you figure out its closest point on the low resolution model, and you do that. You use that to interpolate your signal, which are reasonable for some examples here. But this kind of closest point query may fail dramatically for some pairs like the one shown here. And if your multigrid solver contains some artifacts in the interpolation like the red pairs here, then it will not converge to an accurate solution. So in order to overcome that difficulty, we propose a method to build hierarchy and maintain correspondences at the same time. So here you're seeing like two elephants, identical elephants. And because they are identical, you can easily figure out how to map one point to the other. So it's easy to define interpolation. And our algorithm basically decimate this mesh shown on the right. And at the same time, we keep updating this correspondence information. So at the end of the day, for each vertex shown on the high resolution model, we can figure out its corresponding point on the low resolution model. And I want to point out that this map we maintained here is a bijective map. In other words, a vertex can be mapped to any points in the middle of a triangle. So that after all the queries, we can have one-to-one correspondences between this pair. And the key idea to achieve that is to leverage the intrinsic geometry. So imagine you're like a small ant live on this curved surface, and actually the world around you will look like a 2D plane to you. For example, just like we live on the Earth, we don't feel like the Earth is like a sphere. We feel like the world around us is like a 2D plane. And the same thing happens here. And the key idea is that even if this curved surface are triangulate differently, like the left and the right, but the same region should still correspond to the same 2D parameterization. Therefore, we build an algorithm that computes a shared 2D parameterization for mesh with different resolutions, so that for each point on the high resolution model, we can first figure out its 2D location using this parameterization domain. And because this is like domains shared with the low resolution model, so we can use this 2D coordinate and then query what is the corresponding location on the low resolution model. And that's why we can have correspondences between high resolution and the low resolution shape. And that is basically the key for us to define a multi-grid method for curved surfaces. So take this high resolution shape as input. We can use our method to decimate this model to build a hierarchy. And then for each consecutive levels, we can also use our method to determine the correspondences so that we can define interpolation and restriction. So now now we finally have the privilege to enjoy the efficiency of multi-grid method on geometry processing. So in this case, we're showing like a runtime of solving a single linear system on a curved surface, and you can see that multi-grid methods basically scales much better than the previous used Cholesky solver. And as I mentioned before, multi-grid is also useful for other geometry processing tasks. So in this case, we're doing data smoothing, and simply replace the solver with our multi-grid, we can make it much faster. And also the same thing for physics simulation. So on the left, you're seeing like a balloon simulation using Cholesky, which is slow, but simply replace that with our multi-grid, we can make it 28 times faster. And the same story, the story is the same for other applications. For these applications, we can now make them faster by replacing the solver with our multi-grid method. And the amount of speed up depending on the resolution of shape. If a high resolution shape, then the speed up is bigger. So that basically concludes our last component in this data-driven processing pipeline. And what's next? So right now we only touched like a few examples of easy to use data-driven modeling method, but I believe that there are a lot of other operations that we haven't invented. For example, other modeling operations that can utilize data or try to renovate some existing modeling method with data. And another thing I believe that's important is how can we make those geometric learning methods more robust? Because right now we have actually a lot of geometric data, but those data are not clean. They are not clean triangle mesh with beautiful triangles that we can learn from. They are actually very messy geometric data like this LiDAR scan of the Toronto city. So if we really want to extend the realm of data-driven method to learn on this messy data, we have to make sure the geometric learning method we have is robust to this. And another thing I believe is important is how can we really scale up our geometry processing. So in the rendering, we have such a great advancement that we can now render mesh with billions of triangles in real time. But it is so sad that we are not even able to process triangle mesh with millions of triangles in real time. And it is sad that we can visualize this beautiful geometry, but we don't have a tool to processing them. So I believe the next step is really to scale up our numerical tools or invent new data structures to support large-scale computation. And I believe in the near future, once we solve that challenges, then our general public and some AI agent will be able to know how to model a 3D shape. And because we have such a large-scale geometry processing pipeline, so we can all together model a very large-scale, high-resolution city, for example, together. And for now, I would like to thank all the collaborators and mentors and students I work with, and also my advisor, Alec Jacobson. And thank you all for listening.
Thank you so much for that beautiful talk, Derek. I expected nothing less. We can move forward with our Q&A session. Maybe we should start with questions for Nikan so that Derek can have a time to relax and unwind. So let's see what we have here. So the first question I have is there a reason why these Fourier features, these, I guess, periodic features is how I think of them, why do you think they're well suited for these types of tasks, for tasks like image reconstruction that you showed before, but also topology optimization? I'm just having a hard time seeing how like adding that small feature can make the results be that much better. Do you have any insight as to why that could be?
Well, actually, two different prior works address this fairly properly. One is Siren that we really didn't mention here, and the other one was that Fourier features that we referenced. And although these two methods take different approaches, but what they conclude is that using a mapping that maps a low dimensional input to a higher dimension, for instance, instead of a 2D input to 1,000 dimension input, it enables us to control the target function, the frequencies that the model can learn. And usually because we intentionally use L2 loss functions, it over smoothes the design usually. And by using these Fourier features, we can explicitly control that how many high frequency we want to have. And actually we can treat it like a classic way of treating Fourier features for filtering. That's why it helps actually to have these features in our model.
That raises a good point. So in this case, the person designing the network can choose the type of frequencies you want to see in your output. Do you think, or do you, Derek, also think maybe you can contribute that this type of feature choice could be useful for stylization purposes, like maybe a neural cubic stylization? Or what type of frequencies would an artist want for a neural stylization type of paper?
Yeah, I think that's depends on what kind of style you want to achieve. For example, if you're looking at those cubic stylization, you can see that actually the stylization effect we want to achieve is something that's low frequency. Like we want to make the general shape look like a cube. So in this case, I don't think the Fourier feature will be useful because it will intentionally make things very high frequency, which is not what we want. But imagine if you are doing something like texture synthesis, you want to synthesize some high frequency texture on your surface, then I believe adding some Fourier feature or some positional encoding will be useful here.
I see. Yeah, that makes sense. Thank you to both of you. I have another question for Nikan. Let's see. So what if you wanted high frequency, complicated designs in one region of your structure, but you wanted more of a low frequency design in another region? Or do you think this could be accommodated somewhere in your architecture?
Well, one thing is that we considered in our work was that to make it as simple as possible. For instance, there's no a specific architecture in the neural network or anything else. But what we actually thought that we could incorporate any ideas that you could use on a finite element method into the neural network itself too. For instance, multi-resolution or multi-grid. Exactly, we tried that before, but it wasn't really as good as we expected to be. But yes, there are different methods that we can exactly use it. For instance, one maybe interesting one could be using dozens of a small neural network instead of one big neural network for different regions of the same mesh, and you have full control over explicitly each element of the network, in other words. So yeah, you have full control similar to finite element method.
Okay, thank you very much. Now we have a few questions for Derek, although I do find that these talks mix well. They lead to a lot of questions that I want to immediately collaborate with both of you on. Let's see here. Which one should I ask? There's so many. Is there? No. So there are a lot of mesh convolution algorithms that have been proposed over recent years. I mean, there's tons, each with different sets of properties. I guess I'd just like some insight into where yours fits in all of this. Is yours the only one that satisfies the properties that you mentioned? I have a few follow-ups to that too. So yeah.
Yeah, so I think like you said, there's millions of mesh convolution operations here. And there's something that based on like smooth setting, for example, locally flatten the patch into a 2D and then do convolution there. And there are also some more graph-based or also some diffusion-based method. And for the convolution we talked about today, it's actually belongs to a discrete mesh convolution. Basically, we operate on triangle mesh directly without, I don't know, flatten it or do some spectral method for doing that. So we belong to a mesh-based convolution method. But we are not only the only method that's invariant to the properties we want. For example, in Rana's mesh CNN, then they don't consider this half flat, but they have a different way of making sure this thing is rigid motion invariant by providing rigid motion invariant features such as the angles between the flap. And if you have operate on those angles, then you can invariant to the motion because like the angle will remain the same. And there's also another method from the deep texture synthesis. So what they do is actually very similar, but they are not working on half flap, but they work on a triangle and its adjacent 3 flaps. And they do a similar thing to our setting. They also try to come up some local coordinate system to encode their feature so that they can kind of take this, they can take this orientation information into the consideration. But I think that's the recent ones. And yeah, I think that's the recent ones. And then, yeah, they all try to address the problem of different measure variations, which I think is very important for making this method generalized.
Yeah. As a little follow-up to that, you mentioned before that using a graph neural network, not a mesh CNN, a graph neural network was maybe a bad idea because we would be losing some sort of manifold information. But is there no way that we could perhaps encode that manifold information inside each edge or node and then just use that same graph neural network? Is it just a feature problem, or is it really like a convolutional layer problem?
I think you're right that if your input feature, if we have some way, for example, like the heat kernel signature, wave kernel signature, that we assign feature to the graph that is already invariant to all this kind of deformation or motions, then if you use the graph network to learn that, because your input is like you have no information about the embedding of the mesh, so the method will definitely be input or very rigid motion invariant. But I think the fact that I feel like the graph neural net miss is that you actually don't know that, for example, you're on a surface mesh, you can, for example, in our case, we can beautifully define some local coordinate system to encode our feature. But for a graph, generally the graph, you don't know how it is embedded in the space. And so it is, and also you're operating on a lot of graphs that are social network, which are, I don't know, impossible to embed, for example. And in this case, I think they limit us to leverage some geometric quantities to really make this network suitable for processing geometry. For example, in our case, we leverage the mesh structure of the half flap, we leverage the local coordinate system, but this we don't have this information if you treat your mesh as a just general graph where you don't know the embeddings. So I think there are some, there are some trade-offs here.
I see. Okay, thank you. So one more question for Derek. Also, all the results you show are for a screen, like they're ultimately projected on a 2D image, and all of the applications that you've talked about, like seeing your parents virtually in a 3D world, ultimately that'll also be projected back to you through an image. Maybe you see where I'm going with this already, but is there a reason why you're so focused on coming up with algorithms that operate on meshes instead of images? Do you think it might not be more reasonable to do cubic stylization of a shape projected on the 2D screen directly on your image, for which we have many like image-based neural networks that are very, very strong? What's the argument here for the mesh-based style?
Yeah, I think this is like very tied to, for example, I think the perfect example is to think about how people make animation movies, like Pixar movies. So in order to create those movies, although we're in the movies theater, we are seeing like a 2D projection of those models, but it is, for example, it is hard. For example, if you see a 3D model, like if you rotate the camera and see a 3D model from a different perspective, if you're really doing things operate on 2D, then you have to create each 2D projection one by one. And another thing that's very hard is when you want to make sure the transition is smooth, and you also want to make sure the lighting is like kind of coherent. And so if you work on everything in 2D, and like in this, you will interact with this like 3D thing, and it's super, super hard to make sure it is like without any artifacts and then everything is coherent. That's why in those movie production, they're actually making a 3D model of those characters, and then they're just shooting this movie like virtually on the, I don't know, on some modeling software, so that they can kind of make this movie that is kind of consistent and then beautiful and then coherent. So I think there are still some limitation of doing anything in 2D compared to make a thing in 3D. And then if you want, you can project to 2D. Yeah.
Yeah, thank you very much. And this leads me to my last and final question that I'd also like to hear from Nikan about. So Nikan's work deals with a grid structure. You have a neural network for each pixel, basically, right? It's sort of like a bunch of, it's sort of like a neural implicit, where you have a network that predicts a density field for each pixel, whereas Derek's is on a mesh, not on a grid. Is there a reason why? It seems like we're getting a lot of really good results from using 3D grids as well for deep learning applications. Is there a reason why we might still want to hold on to our mesh-based deep learning tools, or should we just switch to using, you know, grid-based deep learning methods on a super fine 3D grid?
Mm-hmm. Okay, I can start.
Mm-hmm.
Okay, yeah. So I think this is like a very great question and very important topic in this community. What other representation we want to use for different tasks? But my personal view is that I don't think there's a single representation that wins on all aspects. For example, even if we forget about the neural representation, we focus on traditional representation. For example, in digital sculpting, people are still prefer to use implicit function like sine distance field or something like that. But for modeling characters or deformation, then people prefer to use meshes. And for rendering, people also prefer to use meshes at this moment. So I think there are not a single representation that is like good in all aspects. And similarly to the neural thing, it is very good. It's differentiable. It's very good to set up some optimization. And recently, there are still some impressive reconstruction and visualization. But for example, if you want to do deformation, I don't think it's a great tool here for us to really easily deform like those neural implicit representation. So my perspective is that there's still some value to work on different representation, because different representation are suitable for different tasks. And if you only double down on this neural representation, you probably will have some difficulties to do the things we can do today. I don't know, like Nikan wants to.
Yeah, on that, and if I want to extend it, for instance, even in case of topology optimization, you might think we have the governing PD equations. They are continuous, differentiable. Why not solve them using neural networks, since we get, in fact, infinite resolution? Since they are continuous, you can query them at any resolution you want. But the issue is that when you see, in fact, solving those are very tricky. Most of the time they don't work as expected. That's why even though using finite element solvers sometimes reduces your accuracy, or when you choose a very fine grid, it needs a lot of computation, but the flexibility it gives, or the guarantee that you will get a good solution, is always preferred in many cases. I mean, in case of very large examples I've seen for topology optimization, people still prefer the old methods than the new neural network-based methods. So yeah, that's the case.
I see. Thank you. Thank you very much for both of your time and for the great presentations today. That concludes our first session of this season. Let's give it up to our speakers, and we'll see you again next week. So stay tuned for the upcoming poster for next week, and have a good day, everybody.